numerical and method analysis. I'm working with Mr. Qassimi Abdurrahim at the High School, National High School of Artificial Intelligence, Sidi Abdullah, Algeria, and Mr. Ahlem BOUCHERIKHA at the University of Victoria. The title of my presentation is Barotropic and Baroclinic Model. For my work plan, I have introduction and notations and preliminaries. Introduction, annotations and preliminaries, and process design functions, and Galopian projection in the meridional direction. In this work, simplified barotropic and baroclinic model will be used to study motion oscillation and intertropical convergence zone. The mathematical study here will be carried analytically by using the linear theory and numerically. I have for the primitive equation, we consider the following of these equations. Here we have the velocity, horizontal velocity, and the W is the vertical velocity, and F is the force of Coriolis. Phi and theta are the pressure and temperature perturbation. I work with the condition or the rigid boundary conditions W in Z equal to 0 and H equal to 0. And by using the beta plan approximation and the force the Coriolis force F equal to 2 omega sinus Y. And by using the scaling tool, we need to convert the equations 1 to in the non-dimensional by using all this scaling. And we found this system in the non-dimensional unit. Now I will decompose the non-dimensional equation to the shear barotropic and baroclinic. And we found this system in the barotropic and baroclinic mode. And to apply the linear theory, I use the solution V over bar equal over bar 0 equal the shear barotropic U over bar 0. And for the baroclinic mode, I use V1 equal to V1 over bar equal the shear baroclinic U over bar 0. And put some perturbation on the equations. I have V equal V1 and I have perturbation for the V and the theta and V0 and V0. I found the system and because we have the incompressibility constraint, we use the psi prime 0 and replace it by the system. We found this, and we found this. And we, since when we put U prime 0 and V prime 0 like this, and we replace it in the system, we found these equations. And to solve the equation 11 using the Galopian method, which consists of projecting the equations in the y direction into the first few barotropic cylindrical functions. prime 0 equal 3 prime exponential e p to y in the equation 11. And this for the Galerkin projection. When we use the Galerkin projection, we found these equations. And now we plug the shear barotropic equal to alpha 0 y and the shear baroclinic u1 over bar equal to alpha 1 y plus b in the equation. And finally we find the system. And by changing variable y prime equal to y plus f0 l f0 l and by changing this variable, and we go to the radiation condition. We use this condition on the system. And finally, we found this system by using Galerkin projection and by using the condition of radiation. The matrix A over bar, and B over bar, and C over bar, and D over bar, and E over bar, and the submatrix of all the matrix. And now we pass through the spectral method by using the linear analysis of the system wave-like solution W over bar, and we plug them in the equations by using Galerkin projection. And finally, we must find the eigenvalue and eigenvector of the matrix A prime over bar. Now we pass through the validation test. In the case number 1, we put the shear barotropic and baroclinic, and we put the function f equal to 0, and we take alpha 0 equal to 0, and we take alpha 1 equal to 0. And we found the real and the imaginary eigenvalue. And for case number 2, we put alpha 0 equal to 0.2, and alpha 0 equal to 0.5, and alpha 1 equal to 0. And in the case number 3, we take alpha 0 equal to 0, and alpha 1 equals 0.5. And in the case number 4, we take both of alpha 0 and alpha 0 equals 0.2, and alpha 1 the same, 0.2, and we take alpha 0 equals 0.5, and alpha 1 equals to 0.5. And we have the eigenvalue of the matrix, real and imaginary. Here for alpha 0, 0.2, alpha 1 equals 0, and here for alpha 0 equals 0.5, and alpha 1 equal to 0. Here the imaginary for alpha 0 equals 0.5, and alpha 1 equal to 0. And here for alpha 0 real eigenvalue of matrix, alpha 0 equals 0, and alpha 1 equals 0.5. And here for alpha 0 equals 0 and alpha 1 equals 0.5. And here the real for alpha 0 equals both of alpha 0 and alpha 1 equals to 0.2. And here the imaginary for alpha 0 equal to 0.2, alpha 1 0.5. And here for real, when we put alpha 0 and alpha 1 equals 0.5, and finally here the imaginary for alpha 0 and alpha 1